Alright, so let's work on this problem. So we're going to try to find equations for slope and displacement in the beam. So our technique that we've talked about so far is to do what? What's the first thing we need to do?
Moment.
We need to write a moment equation for this. So if I were to cut this structure at some position, let's just say I'll cut it here, and I look internally some distance x, you want to work the right side or the left side?
Do the right side.
No, let's not listen to Mr. Abney on this one. Let's do the left side. So if we're going to do the left side, let's find the reactions at A, which would be the shear at A and the axial force at A. So to do that, I'm going to sum moments about B. And to make that easier on myself, I'm going to first find the concentrated equivalent force for my distributed load. It's a rectangle. So the area of the curve is base times height, so this will be WL. And of course the distance to the end will be L over 2. So that's all the information I need to find my reaction or my shear at A. So I will sum moments about B, make sure I'm in equilibrium. When I do that, I've got the effects of this concentrated load, which create positive moment. So there's the force WL times the distance L over 2. And then my reaction creates negative. That's the shear at A times W. And surprise, surprise, the shear at A is WL over 2. Basically half the total load.
What would be the difference if we did the over at A?
You'd get the reaction at B, which we don't need. Then you have to sum forces in the y direction to get A. We've decided to work the left side, right? Yep. You see that? Okay, so now I'm going to draw a free body diagram of this side, just like we've done before. And I'm going to put on that I've got this shear force of WL over 2. What else do I have? I have the distributed load acting over the beam, which has a value of W. What else do I have? I've opened the beam up, so I have my internal stuff. I've got the moment and I've got the shear. Now, I don't care about the shear right now. I just want to find my moment. Oh, and also this is at an arbitrary distance x from the left hand side. So again, I can find my concentrated equivalent. It's the area under the curve, right? Rectangle, that's base times height, so that'll be WX. And what's the distance between this force and the cut?
X over 2.
X over 2, half the distance. That seems to be all we need for that. So again, let's sum moments using right-hand rule as our sign convention. And I'll do it at this arbitrary cut distance X. Starting at the left-hand side, I have the moment, internal moment. This force Wx creates positive moment. So there's my force Wx times my distance x over 2. And then I have my reaction creating negative moment, which is WL over 2, and it's times a moment arm of x. So from all that, I should be able to solve for my moment. Let's see. I'm going to get minus WX squared over 2 plus WLX over 2. Does that work? Well, where do I know the moment in my real beam, my original beam? Well, at A is a pin. What's the moment at an external pin? 0. So does my equation tell me that? Well, when x is equal to 0, I get 0. Do I know it anywhere else? Over here at B, I know it, and that's at x equal L. If you put in x equal L here, you get 0. So it seems to work okay. So I'm halfway, well, not quite halfway through, but I've got my moment equation. All right? So up until a week ago, this is where you'd stop. But now we're just getting started. Isn't that exciting? So now we come down here and I say, well, the slope is the integral of the moment divided by EI. In this particular problem, we'll assume that EI is constant, which it usually is, not always. And then I'm looking at the integral of this equation, which is minus WX squared over 2 plus WLX over 2. So let's do that integration. Again, I'll leave my 1 over EI out. And let's see what we've got. So I'll integrate this, so that'll be minus WX cubed over 6 plus WLX squared. Oh, I messed that up, didn't I? That should be over 4 plus an integration constant. Oops. I need my tape to hold my sheet down. Sorry about that. Do I know anything about the slope in this beam? Do I know something about the slope at this support A? No. It can be anything. I know the displacement is 0, but not the slope. What about at B? Same. I know the displacement, but not the slope. Now, some people will say, hey, this is a symmetric loading, so that means the maximum displacement will occur in the middle. What's the slope at maximum displacement? 0. So I could match this equation at x equal L over 2 and say it's equal to 0. But at this point, I think that is not a good idea. I think I just leave it alone, and when we get through, we'll check the final equation for displacement at 2 points, at A and B. So let's do that.
The slope of A and B will be equal to each other, right?
In value, but different signs. You'll have negative slope at A and positive slope at B. So if we just leave it alone, and we come down here and we say y is equal to the integral of slope, then what do we get? Well, we still get 1 over EI. And I'm going to integrate this. So the first thing I get is WX to the 4th over 24 plus WLX cubed over 12 plus C1X plus C2. So I have an equation for displacement that has 2 constants in it, but I have 2 conditions to match it. So we're okay. So let's do that. So I know that the displacement at x equals 0, which is what? Point A. What is the displacement there? What's the displacement at A? 0. So I plug in x equals 0 here. 0, 0, 0. What do I get? C2. So therefore C2 has to be 0. I know that the displacement at B, which is at x equal L, is 0. So now I got to plug x equal to L. First of all, since this is equal to 0, do I care what EI is? No. So I'm just going to plug in L, L, L and see what I get. So I'm going to start off, I'm going to get negative WL to the 4th over 24. I also suggest you take your time and do this slowly. And then you get plus C1L. And that's equal to 0. So you should be able to solve for C1. So what is C1? Well, first, if you divide through by L, everything is L cubed. You can divide through by W, right? So I end up with what? A negative 24th plus a positive 12th. What is that? That's a positive 24th, right? Because if I change this to 24, it's 2 24ths. So I got 1 24th plus 2 24ths is a positive 24th. I throw it to the other side of the equation. I get W L cubed over 12. Oh, 24. Okay? Everybody see that? The silence is overwhelming. Is that a good thing or is it a bad thing? All of you scratching your head and rubbing your hat, I'm just wondering, is that a good thing or a bad thing?
Not too bad.
Or is it just forgot to shower this morning?
Just accept it.
It's a lot of things.
Now that you're going to call me out like that.
No, I was talking to Mr. Wilson, actually.
No, it's fine. We're just flat. Okay. You move the...
All I did was satisfy one condition and two conditions. I'm forcing my equation to go through those 2 points.
If you get a positive 24 over to the right side and a negative 12, that would be...
Well, I end up with 2 negative 24ths plus a 12th. That's 0. Right? It has to be equal to 0.
Okay, I see.
That's what I'm saying. Just take your time. It's just algebra. Just relax. Because when you're done, both these values have to be shoved back into the equation. So you can see that C1 is going to go back and affect your calculation for slope and also your calculation for displacement. So I'll just stick it back in the displacement equation and give you that. So what do we got? So I put this back in here for C1. It looks like I've got a W and a 24. That's pretty common. And actually an X. So I could kind of write it like this. I could say W X over 24 EI. And then what do I have left over? If I look at the first term, I've got minus X cubed. Look at the second term, I've got plus 2x squared L. Now look at the C1 term, I've got minus L cubed. I think that's it. Now, if you look inside your front of your book, and we look this problem up, we got the right answer. What they did is they just pulled the minus sign out and put a minus sign in front, but it effectively is the same thing. So that would be the displacement. That would be our equation for displacement. And we could also go back and get the one for slope, but I'll let you do that one. Now, one thing we could ask ourselves is, where's the maximum displacement in this beam? Well, we think it's the middle, but mathematically what we would do is we would take the slope equation and we would set it equal to 0 and find what x value gave us 0 slope, right? And then plug that x value into the displacement equation to find the maximum value. So if I gave you some load function that was not symmetric, then you would have to go that extra step to find the maximum displacement.
Can you say that again?
Well, remember that usually the maximum displacement will occur when the slope is 0. Right, so your curve is coming down to a maximum displacement, and when it does that, what happens at that point? Right, the slope is 0. It can do the same thing going up. You might have 2 of these. Unlikely, but in our problems, usually there's just one. But it's possible under some very strange load condition that you could have a value, you could get an equation with multiple values for x. And you probably will anyway, because you'll notice that this is a cubic equation. How many values will you get when you set this cubic equation equal to 0? You'll get 3. But 2 of them will not make sense. You'll have an x value that might be negative. Or you'll have an x value that's greater than L. Doesn't make sense. So there's only going to be one physical one that exists between 0 and L that will make practical sense. And then that's the value that you would put in here to find the maximum displacement. Mr. Abney.
Will we have more than 60 minutes on this test?
No. Any other questions?